Welcome to example number 11. In this question, we are looking at calculating the power of an automobile that is accelerating down the highway. So let's start out by writing our known and also get a little picture shown as well. So we have a car starting off with an initial speed of 30 kilometers per hour. And then finally, after 10 seconds, it reaches a speed of 100 kilometers an hour. And the time that it does this in is in 10 seconds. Okay, we can write down our given over here as well. We have the mass, 1,200 kilograms. We also have the time that are indicated over here of 10 seconds, the initial speed, 30 kilometers per hour, plus the final speed. And we have to calculate the power. So we're finding P. Okay, so as you recall in the earlier video, power is defined as the rate of doing work, or also the rate of change of energy transformations. So power is equal to delta E all over delta T. And in this particular case, the car is gaining what kind of energy? Hopefully you realize it's speeding up and hence it's gaining kinetic energy. So this change in energy here is really equal to the change in kinetic energy. That's delta K here. And to calculate the change in kinetic energy, we would need to know the kinetic energy finally minus the kinetic energy initially all over that time period. The final kinetic energy can be calculated by using 1/2 mv final squared. The initial kinetic energy is 1/2 mv initial squared all over delta T. Oh, I've labeled just V final as just V and V initial as V sub 0. So I'll just put this as V squared and V initial squared. If you'd like, you could also take out common factors. So I'll take a common factor of 1/2 and m and delta t. So it's m over 2 delta t times v squared minus v initial squared. Okay, and then now it's just a matter of plugging things in. Probably the most common mistake that people are going to make with this problem is actually not necessarily the setup, but really just actually realizing that your energy, we would like it to be in joules per second or watts. And a lot of people will forget to change these velocities over to meters per second. To change those velocities, we would need to convert from kilometers to meters, so there'll be 1,000 meters on top and 1 kilometer on the bottom. And then we also have to convert from hours to seconds, and there's 3,600 seconds. So essentially you would be dividing by 3.6. And that will give you a speed of 8.3 repeating meters per second. And then similarly, you could do that for 100 kilometers per hour. The speed of 100 kilometers per hour in an hour would be equal to 27.8 meters per second, or 27.7 repeating meters per second. And now you just need to substitute these values into your equation. And there's the substitution. And then go ahead and put on your calculator. And I get an answer of 42,129.6. So maybe I'll just round that off to approximately, because if you look at it, I have 2.6 or 3.6. I'm just going to round that off to 42,100 joules per second. Or you could convert this to, this is about 42,100 watts, or you could even say that is 42.1 kilowatts. And you can see over here the answer is also listed in horsepower. If you were to convert this to horsepower, you would use 1 horsepower all over 746 watts, which gives you about 56.5 horsepower. I'm not sure which one is the more correct answer here, but they're both close enough anyway. Just to point out, this is not the only way of solving this problem. There's many other versions. I've done this problem before with students in class, and I find that there are some people that will take the approach of using power equals force times velocity. Now, they have a little bit of a problem here. They using this approach. First, they have to figure out the force. To find the force, you have to use mass times acceleration. Before you can find that net force, you have to figure out the acceleration. The acceleration is the change in velocity over the change in time. So it can be quite hard. And then also this velocity. What is this velocity? This velocity is not the starting velocity, not the final velocity, but that's the average velocity. So that's one approach. There's other people that use, you know, you've got power equals work over time, and they do force times distance all over time. And they have to, in this case, you have to find the force, and then you find the distance through kinematics. So lots of different ways to solve the problem. I think this is the easiest way that I've just shown you, the fastest way I think to get the answer. But the more ways you know, the better it is. Okay, that's it for example number 11.